So, welcome everyone to today's StudyTank session. I'm Nonso, a software developer and one of the community organizers here at TechTank. Part of TechTank is our StudyTank initiative, which is a virtual space that allows where we get together to discuss things around web technologies and other concepts related to the web. This includes, but is not limited to, data structures and algorithms, web fundamentals, and really any web related topics itself. Recently, we started the Community Educators Program, which really invites members from the community to teach about topics that they are really passionate about, as we believe that the learning journey is not just about acquiring knowledge, but it's also about how we effectively communicate the things we've learned. Tonight, we have an awesome session by Neil, who's going to be talking to us all about containerization. At the end of the presentation, you'll have a chance to ask Neil questions, and you can either do that by typing it in the chat or muting your mic during that time as well. So, without further ado, let's welcome Neil up to the panel. Hey, Neil, how's it going?
Hello, not too bad. Um, I hope everyone's ready for this, and I'm honestly hoping this is not an information overload, but let me just share my screen. So, welcome everyone to Containerization 101 by yours truly. I always like to start off with a little about me. I started, and this is more so you have an idea of why you should li maybe listen to me, as well as why maybe you shouldn't listen to me. It's up to you to decide. And um, I basically started programming and web development in grade seven because I had a simple problem to solve, and that was our school board blocked Miniclip, and I needed to play my games at school. So I went home, looked up how to build a site, and then pirated the games onto it. That's how I basically got started, and ever since I've been self-taught and I've followed wherever my curiosity has taken me. And that's my learning process. I will tinker with something, whether it be software, hardware, anything that piques my curiosity until I eventually break it, panic, stress out a bit, and then fix it. It's my learning process, and I do truly enjoy it. If you want to learn more about me or get in touch, my site is called drunkensorry.com. You're free to visit it at any point, and that's that. So the things we're discussing today is mainly in three main sections. The first one is Intro to Containerization. This is more going into what containerization is exactly and why we use it for software development. The second part is Docker. What is it, and what are some of its key features? The third is the best practices and considerations, or as I like to refer to it as the roadmap to not becoming legends at work for all the wrong reasons. Um, and finally, Q&A. I did have a very basic live example that we'd be doing in between as well, but depending on the time, I might not get to it. So, so onwards to the first part. So, intro to containerization. I like to refer to containerization as the software equivalent of instant ramen. Why? Well, if you think about it, a container is basically just a lightweight, isolated part in your system that has it's running the running app, any dependencies, any runtime environments, and any libraries packaged within it. And it will consistently run on supported computing environments and basically just anywhere that containers are supported. The direct equivalent to that in real life is an instant ramen. If you take multiple containers of instant ramen and make them, the output will always be the same and it'll technically always be in roughly the same amount of time if you're using water from the same kettle. And when we're looking further into it, the easiest way to go into why we use containers is to look at issues that exist with traditional development and deployment processes. So, one issue that we've battled with for years was ensuring compatibility across operating systems. Sometimes you had, especially in some languages, you had issues where if you developed specifically on Windows, when you deployed it onto Linux, you missed some parameters here or some um, environmental variables there. You had to manage dependencies manually. Deployments had variability in it because the way a server configured could vary between the physical servers themselves, because someone missed a random line in a Nginx configuration file or something like that. And then replicating your development environment as a developer was a massive pain in the butt because you essentially had to manually download all your dependencies, set up all the essential basic configurations, and ensure it's a one-to-one copy to what your company or your systems require for you to develop. So the advantage that containers brought to the development process is that one, there's a focus on helping you write code rather than worrying about making sure your development environment is the same environment that you need. It took away the environmental inconsistencies. It brought you the ability to actually test your software in a simulated production condition. If you want, you can run 1,000 containers on your laptop. Will it survive that? I don't know. Should you try it? Probably. It'll teach you something. But it's it's very flexible in what you're capable of doing. You can um, also package whatever you're working very easily and then share it with other devs or other people that need access to it without them needing to set up anything. On the DevOps side of things, it streamlines the deployment process considerably. So, because a container creates consistency across different environments, you can deploy at scale very easily. Then containers by design are very naturally isolated. This isolation also means that, unlike a traditional monolithic system, if one container fails, it's not going to bring the entire host and any other containers within that host down with it. So, what do I mean by that? In a traditional system, you'll have a front-end server, and you might have the database on the same server, on the same physical hardware. And let's say the front end server created a memory error and it errored out. That error could transfer over to the database and bring it down along with everything else. When you do it in a container, only that container goes down. And the way containers are designed, they can be immediately restarted with next to no downtime. So in most cases, unless you're the DevOps team in charge of monitoring those, you'll never know it even happened. The other thing with containers is it's very efficient. You don't really lose any performance when you use them compared to just running it on native hardware because they share the OS's kernel and hardware resources. And the final advantage that it brings to DevOps anyway is it encourages the use of infrastructure as code. For those of you that don't know what that means, it's basically the ability to now define your entire production deployment, including your servers, how they should be defined, etc., in the cloud in code and then being able to version control them so that you have one source of truth for your entire deployment pipeline. It makes troubleshooting easier, it makes finding security issues easier. It basically simplifies a lot of things that we take for granted. But some of you may be going, doesn't containers just sound the same as virtual machines? And on many levels, yeah, they're very similar. But the main difference between a container and a virtual machine is once again, the container shares the host's resources, whereas a virtual machine emulates an entire kernel and an OS on top. So you have multiple layers now that need to translate, and this uses up a lot more CPU cycles and GPU cycles than running a container. In some cases, running a virtual machine can just crash your entire system. Um, the other advantage is starting up a virtual machine is depending on how powerful, for example, your local computer is, can be anywhere between 30 seconds to a minute. Starting a container is under a second in most cases. And the other complication is if you're trying to use virtual machines at scale for some reason, getting them to network with each other is a whole other level of pain in itself. So that's the general basics of what containerization is and what containerization specifically brings to the table when you're a software developer or when you're in DevOps. But let's talk about the most commonly found one, and that's basically Docker. Docker was founded in 2013, and its main parts, the Docker engine, is open source. The reason it is so commonly found, even though there are other alternatives out there, is that it was revolutionary. Containers existed before Docker, but what made Docker special was it made creating, deploying, and managing containers extremely simple and standardized. It made it user-friendly using a very simple to use command line and gave you the ability to store the images in a central repo from where anyone can just pull it. It single-handedly made containers more accessible and easy to use for more software devs. The downside of this, though, interestingly enough, is a lot of the developers that use Docker on a day-to-day basis don't actually know about the different components that work in the background to actually get those containers going, because most of you are just taught to copy the command that your DevOps team gives you and then run it, and you just follow that. It as you progress in your careers, it's generally a good idea to know how all of these work together in the background because it changes how you start developing software in the long run. So this slide here represents the Docker architecture. It runs as a client server system where um, Docker itself works as a server, and you have the Docker client with which you communicate with the server. This is why you can control it over multiple networks, multiple physical hardware, etc. Then the main components that you will interact with are the ones shown on the screen. So the Docker engine, Docker images, Docker files, the Docker registry, the Docker networking system, Docker Compose, and finally, Docker Swarm. I'll be going a bit more in depth on each in a second. So we're starting with the Docker engine. It has three main components. The first one is the Docker client, and that's what you typically interact with when you run your basic commands like Docker run, Docker stop, Docker remove, and all of that. You're basically typing in that command, and the Docker client takes it and sends it to the Docker daemon using the Docker API. So the Docker daemon is basically just a fancy way of saying there's an always running background process in your system that's in charge of starting, stopping, building, and everything else that's related to a Docker container on the host, in most cases, your local system. Now, I have an asterisk beside building because Docker is separating the building part out into its own component called build X, but the way it works is still the same, so there isn't going to be much of a difference. And then finally, there's the Docker API, which the client and the daemon use to communicate. And it's just a basic REST API, but it provides a standardized interface for performing the various Docker operations. Now, because you have this API, you can theoretically build your own tools um, to do all of this instead of using the standard Docker client if you would like. And other tools that some of you may be aware of, like Kubernetes, use the same Docker API to basically control and configure these containers. So now that you have an idea of how the Docker engine itself functions, let's get into Docker images. Docker images are basically, um, in a very simple sense, immutable um, files. They're by immutable, I mean they're read-only. They're used to build containers, and that's all they do. It's almost similar to a save file in your favorite video game. It's a very quick way to start up something from the exact moment you wanted to start it from, if you made the image in that moment. So it's made up of numerous layers, with every layer depending on the layer below it. Um, Now that I'm seeing this list, it should have been the other way around. So the application layer would be at the top, and that's dependent on the dependency layers. You can have multiple dependency layers that are codependent. And then finally, the base layer, which is usually a Linux operating system of some sort. And that's really it for a Docker image. There isn't much more that goes into it. It's made in a YAML file once it is made. Docker files are basically what you use to build these Docker images. They're a very basic text-based script with instructions for building them. It specifies the kind of base images you want, any environment variables you have, any dependencies, any additional commands, and they use very simple syntax such as from, run, copy, command, and entry point. There are a few more, but these are the more common ones. And on the screen, what you're seeing right now is a very basic Docker file. It's to run a Hello World server. And if you look at it, the first line is defining from which base image I want to start the Docker image or want to build a Docker image. And as Hello World stage is setting what stage of the build process I want this to be done at. Um, then I'm setting the work directory in line 3 within the container. Line 5 is basically copying my dependency file for a Golang based application into the container. And then line 6 is downloading those dependencies. Line 8 is copying all the remaining source files from my computer into the container. Line 10 is building the executable from the Go source code. And finally, line 12 is telling Docker that that container should be exposed on port 4000 within the Docker network. And finally, line 14 is running the executable so the server starts running. A Docker file essentially looks like this. On very complicated systems, it can be very long. It can also be shorter than this, depending on how the system is architected. This is just there to give you a basic idea of what to expect when I talk about a Docker file. The next main component that comes into play now that we know about Docker images and Docker files is the Docker registry. Very simply, whenever you create an image, the image requires a storage location. By default, it is your local PC. But if you're pulling images, for example, by default, if it doesn't exist in your local PC, it'll just pull from the Docker Hub, which is hosted and maintained by Docker. You can self-host your own, and that's what a lot of companies do. And anytime you create an image, you would just run a push command, kind of like you're pushing code into Git, and it'll store it there. And it is basically Docker's version of um, bringing some kind of version control to these images so you can keep track of what version is actually available for you to use. Beyond that, the part that makes Docker do everything is its networking component. Without it, all the containers are actually useless. The networking component basically helps establish the communication between containers as well as between Docker, the containers, and the host. So there are four main types. It's technically five, but the fifth one, because it's so rarely used, I haven't included on this. But it's four main types. None basically disables any networking between containers. So, for example, if you have a front-end container and a back-end container, and you booted up the Docker network with the none network type, they wouldn't be able to speak to each other. Um, the bridge is the default. So the way the bridge usually works is um, the containers can talk to the host depending on how you define or how you define the ports assignment. So for example, when you start a container, you can be like port 4000 on my local host should be port 4000 within the Docker network, at which point both of those are joined. Um, and then the host type of networking is used when you don't need any kind of isolation between the container and the host. So at that point, if you run a container in port 4000, that's directly port 4000 on your local host. You don't need to specify anything else. Generally, you don't want to do this because you're taking away one of the advantages of having a container, which is isolation. And finally, is the overlay. So overlay networking is what you actually see when there are deployments at scale. So when you have large swarms of um, clusters of Docker containers and hosts that are being managed by a DevOps team, for example. The other component or the next component that you would more commonly run into as a software developer is Docker Compose. It's very common, um, and the reason for it is very simple. It lets you define how you want multiple containers to start up at the same time and then run as a single service. Um, you have the normal isolation between containers and hosts, but when you run it this way, all the containers within the Docker file can freely talk to each other. The file itself is written in YAML, and I've included a link in the slide for an example of a file. I'll very quickly show it on here, but um, it's a lot to actually go through. So I'll just very quickly just describe what it's doing and then move on for now. This file is for my personal password management service that I use and self-host. It's called Vault Warden. So the file itself launches two containers. One is for Vault Warden and the other is for Caddy. And it defines a few parameters like what image I want to use to build the container name, how I want it to react if there's an error with the container, and things of that nature. If we get time at the end, I will go a bit more in detail over this. The final common component that you'll run into when you come into contact with Docker or when you're using Docker is Docker Swarm. Essentially, it's a tool to manage multiple containers over different hosts, different locations, different hardware, and it simplifies running and managing these containers at scale with bringing things like scaling, um, some network discovery, and a few other things. Um, the weird thing is, even though this is built by Docker and it's a tool by Docker, it's not actually used a lot for large scale deployments, especially when you're talking about thousands of containers over many networks and hosts. The alternative that's actually used in the industry is called Kubernetes. I'm not going to go into too much detail on Kubernetes today because that itself will take a couple hours. But essentially, Kubernetes is used because of a few things. One, um, it supports more than just Docker containers. It supports many different type of containers. And two, um, it just has so much more community-based support and integrations and different ways of doing things compared to Docker Swarm that it's a lot more flexible. The downside with it is it has a massive learning curve, and initially getting it going can be quite difficult if you're not someone who's within the DevOps realm. Um, those are essentially what makes up Docker and what makes Docker tick. They now Docker isn't the only thing that runs containers for the web. There are two main other alternatives that exist. One is called Podman, and it's made by Red Hat, which also makes Linux distributions like Red Hat Linux or CentOS. The main benefit that Podman offers over Docker is Docker requires root privileges to run. This can be insecure because the application that's essentially connecting to the internet has full access to everything on the underlying hardware. There are ways around it, but it's a little annoying at times and can get complicated. Podman doesn't have that issue because it doesn't have a central background service like the Docker daemon that does everything. It only requires sudo for some activities that require escalation. The other benefit provided by Podman is that 98-ish percent of all Docker containers are directly cross-compatible with Podman and vice versa. I say 98-ish percent because you'll find the odd container here and there where there'll be weird networking issues and things like that that it's not really worth troubleshooting. So you just generally stick to Docker at this point. Then the other one is called Containerd. It's the industry standard container runtime by Cloud Native Computing Foundation or CNCF. Now, this is a little bit of a lie. And the reason I'm saying that is Containerd was actually developed by Docker. It was then open source and then handed over to Cloud CNCF in 2017, I believe, or 2015. It's one of those. And in essence, what this means is Docker itself, at its very lowest level, uses a lot of Containerd and how it functions to get everything going. It's just it simplified everything. So the reason you wouldn't want to use Containerd as a normal software developer, for example, is it's extremely low level compared to Docker. It's going to require a lot more effort to manage and maintain. And generally speaking, unless you have an entire team to do it, you wouldn't want to do it. And even if you have an entire team to do it, at this point, it's not worth the effort. You're not going to get much of a performance difference or any differences, if I'm being perfectly honest. So I did have a live example to show. I'm going to leave it towards the end because There's a few more things to cover, but at the end, if we have enough time, I'll go over the example. If not, we will email everyone who attended tomorrow with just that, so you can download it and run it yourself. So now that we've made it this far, the first thing you should keep in mind is URL legends. The second thing you should keep in mind is you shouldn't be legends at work for all the wrong reasons. And when it comes to containerization, and this is a little bit of a pet peeve of mine and something that frustrates me to no end, um, is people looking at very quick tutorials online and then deploying containers with usually some key problem here and there. And I've listed most of the common ones that I see. The first one, interestingly enough, is when you have complex microservice architectures. Containerization basically is what allowed you to do microservices the way we do it these days with its scale and sheer power. But containerization also introduced an additional layer that needs a lot more managing. There's things like service discovery, load balancing, fault tolerance for when containers fail, distributed tracing to figure out what's going on from A to Z, and more. And this needs to be considered as part of the development and architecture process, not once the development architecture process is done. In terms of the term service discovery, basically all it is since containers can start and stop very quickly, you need to have a service that constantly keeps track of new containers and old containers, and then tells everything else that they exist. Um, the second problem is security. It's very easy to get security wrong. Container escape vulnerabilities are simple. Um, what this means is you basically stop getting the benefits of isolation. One way is accidentally launching something as a host or a host network, because then you don't have any sort of network isolation. The other is, for example, having a volume of data that is persistent and transfers to your local host or your local PC. Now you have an avenue for any malicious data that was dumped in there to be transferred into your main operating system. Um, it's generally just following your basic security practices at that point. Because sometimes people think containers just have everything sorted out and you don't need to worry about it. You still need to be worrying about all of those things. The additional things when it comes to security, as you grow in scale, you should ideally be making sure your images are from verified sources and they're scanned using known tools for known vulnerabilities. And you should adopt what's known as a least privilege permission model. This basically means do not give anything more permission than it needs. The more permission something has, the more something can go wrong. So always give it just the right permissions and nothing more. And then the final bit when it comes to security is, and this is more when you're at larger scales, you want to have some kind of real-time or runtime based container scanning to identify for outdated libraries that are still in circulation, outdated dependencies, and things like that, especially if you have containers that have been running consistently for months at a time. A few more common concerns is when it comes to monitoring, logging, and the bane of my existence at this point, troubleshooting containerization. It's extremely challenging since, as I previously mentioned, containers can spawn and terminate very quickly in a matter of a second. They can also scale up and down very rapidly, and they can do a lot of cool and interesting things. But then, how do you monitor exactly what's happening and where it's happening when traditional tools aren't really designed for it? Um, you basically need to figure out some way to have full A to C visibility from, for example, a request being sent by a client to your backend server to it trickling all the way down to the various different containers and then responding back. And there are some tools that help with it. Some like Sentry can help with the tracing, but more often than not, what you end up having is multiple tools, and then you need to put the logs together to figure out what's actually happening. It gets very complicated, it gets very annoying, but it is the way it is right now, and we don't have anything better currently. The final part that I see people make mistakes commonly is data management and persistence. So containers are ephemeral. What that means is it exists in that moment in time, but any data within it only exists in that moment in time. As soon as that container stops, it's gone. If you don't have an external volume defined for persistent data, that data can never be recovered again. There's a container when it starts up again will start at whatever its original image was set at. So this is something to be very careful of. I personally lost a lot of data in my early days because I kept forgetting about it when I started containers. And then finally, just some very basic miscellaneous best practices is Docker files should be as simple as possible. The lesser the layers, the better the build performance. What I mean by that is I very commonly see files that might have 4 run commands back to back. When you have 4 of those, Docker is basically going to be building and running that file line by line. You can combine it into a single line. This starts mattering when you have Docker files that are hundreds of lines long in some cases. You should never hard code sensitive data into Docker files. You should use tools that are available for it, like Docker secrets or even just environment variables. Um, it's very easy to have excessively large containers instead of having a resource efficient container. What I mean by that is, for example, if you're using Go, if you're building the example that I was going to show you, um, it's very easy to build an output container that's 1 GB in size. And it's also very easy to get an output container that's 15 megabytes in size, and it's doing the exact same thing. This is where you use multi-stage builds, where you first use a container to build out your final output, and then use a second container to pull only the output itself and leave all the binaries, all the unnecessary files and things behind. And then you just close the first container. The and this Docker file actually shows you an example of what I mean by that. If you look at lines 1 to 14, that was technically the original version of the Docker file I showed you. That would have outputted a 1 GB container. Line 16 to 24 is now doing a multi-stage build where after line 10, it goes straight to line 16. It starts up a new container using Alpine Linux as the base. And then it pulls on line 20, it copies the executable file called hello world from the original container into the final container, and then does the same thing it did previously, where it exposes the port and then initiates the application. And that is really it for the common issues and problems that I see generally when I see people using containers. Nonzo, I'm not sure how we're doing for time. If we have time, I can do a quick demo. If not, we can go straight to Q&A.
Well, first of all, thank you so much, Neil, for this presentation. It was really, really insightful. In terms of questions, does anybody have any questions for Neil? You can either type them in the chat or you can use the raise hand feature and we can take your question live. Igor, you have a question? You can
Yeah,
unmute
yeah. Thank
yourself.
you, Neil, for the presentation. I wanted to ask what would you recommend as a discovery service? Something that would link all these microservices together.
So if you're so I okay, this is where kind of Kubernetes. This is also part of the reason why Kubernetes is used so much when it comes to this. But I also hate recommending Kubernetes, especially if it's at a smaller scale. So Kubernetes has built-in service discovery. It has built-in auto scaling. It has a lot of useful tools to make your life simpler built into it. But the problem with using it as well is it now adds an additional abstraction layer on top that you need to be aware of. And when you're troubleshooting, you need to keep that in mind as well. It basically tendency to overcomplicate things without actually um, gaining too much of a benefit. Now, when you're running something at a smaller scale, you might not even need auto discovery in some cases because when you deploy it, you can always set the containers to restart immediately if there's multiple, if it's experiencing an error of some kind. And if you're having a cluster of them that's doing the same thing, it'll still handle your load unless you're experiencing massive spikes of some kind. Um, I hope that helps answer the question.
Yeah, yeah. Thank you. Yeah, I was thinking more about like all this like service mesh stuff, but essentially you're right. Like Kubernetes, like there's a way to create a service with a unique name, right? And then link stuff just using service
Yeah,
names.
at this point, like if you're going to do it at this point, as much as I hate to recommend it, it's probably the way you should do it because that's how everyone else is doing it. And if you're doing DevOps as a career, especially, or considering it as a career, it is the way to go, essentially.
Thank you.
You're welcome.
We had a question in chat from Buka. They said, as you mentioned, it's important to think about memory persistence. In your opinion, what's the best solution to save data?
Simplest solution is basically mount. So at a very basic level, if we're going back to my Docker compose file that I used earlier, um, at a very basic level, you can just save it to a folder in the physical host itself. So, for example, in this, I don't know if you can read it, but I've defined a volume within a folder called vw-data, and that's the persistent location for anything that's saved within the data folder within the container. And then if you're doing it on a cloud architecture, for example, within AWS or something, um, you would just set it up so that that's part of the persistent EBS storage or whichever storage you're actually using. That would be the simplest way. But then as you start scaling, depending on the architecture and things like that, it will change. Um, and it's going to vary how you actually do it. I hope that helps.
Awesome. Did we have any other questions for Neil? Shivam, you had a
Yeah,
question?
Yeah, thank you so much. So, my question is actually I'm building a Node app with like Postgres as a database, and I want to like deploy it. So, like I have used Postgres image for I'm using my Postgres image. So, like, but I'm confused with like how can I deploy it? Like, how can I deploy them together so that I can use it in the front end?
So, simplest way is, um, hmm, actually, there's I think the most straightforward way is when you're setting it up, you'd want so within Docker itself, and you'll need to look up the exact term for it. But within Docker itself, there is dynamic networking, so you can always identify the network path within Docker's network that different containers are on. So if you're launching them as individual containers, um, you'd essentially be pointing your uh, um, whatever server speak or whatever container speaking to the Postgres container uh, to use the Docker specific network, and um, it'll just get passed right on through. If this is more on a larger scale of things, as the containers are being deployed, we come back to the service discovery mechanism where it acts kind of like an internal DNS system, where anything that's deploying would kind of ping it to figure out, hey, where is something located, get that location, and then communicate directly with that location. Does that make sense?
Yeah, actually I have created a like YAML file like Docker. So I am deploying them together. So I've created a network where like my Node app and like Postgres app are going to be running in the same network. And then like I'm going to deploy it. So that was the thing, like how can I deploy them together? Like they are in the same network.
Okay, so if they're in the same network, and if you're trying looking at so you have a Docker Compose YML file is what I'm
Yeah,
understanding, right?
yeah.
Okay, and you basically need them to talk to each other. Is the is the problem, or am I
So no,
understanding?
they are able to talk, but like I want to deploy them on a server so that I can make them to talk to a front end application, like maybe React.
Okay, so in that case, you'd basically need to define the ports that your Node.js server needs to be listening to. So once again, let me just see if I can zoom into this. One sec. So if you look at this here, I have my ports mapped in my Docker Compose file.
Yeah,
And it's basically saying anything that's coming to the host at port 80 should be forwarded to port 80. And since it's set under caddy, this is automatically assigned to caddy. The same thing with 443 for SSL. And once this is done, if your Node.js instance or server is properly listening on those ports, everything should theoretically just work.
yeah, that makes sense. I will try this thing.
Awesome. We had a question from Curtis who asks, is it useful to learn Docker regardless of what branch of IT you're in?
Yes, highly recommend it. So, um, the reason I say that is containerization isn't limited to the web. So, Curtis, I'm just because I'm using, so what you're seeing on my screen right now is Linux. I use Linux as my main operating system. I've used it for almost the past decade, I think longer actually. And I right now have containers within Linux that boot up different things when I want to isolate stuff within it. And it uses a mechanism built by a Linux distro called Vanilla OS, and I believe it's called aptX, um, not to be confused with Qualcomm's aptX codec. And what it basically is doing is natively having a mechanism within my Linux distribution where if I want to, let's say, test with something where I'm not really sure if it'll be a security vulnerability or it'll infect my other files, I can very quickly use aptX to boot up an entire separate Linux container, which acts natively like it's just running as part of my operating system. I can even install, for example, VS Code in another distribution within that container and then run it natively. It's a different kind of container, but the general operational principles when you're programming and building something like that is the same. There's another Linux distribution called BlendOS that is also trying to do the same thing, um, albeit slightly different implementation. And all of these start kind of from the same spots. Not necessarily Docker, but from containerization. And understanding all the limits that containerization with Docker gives you will also give you an understanding into everything else. And then once you learn Docker, if you want, you can go further into lower level things like Containerd and stuff like that. The other bit is if you're curious about it, explore it. It never hurts to learn.
Awesome. We had one more question here from Mark. It looks like Larry is already answering it, but it would be awesome to get your thoughts as well. The question is, would it be redundant to have multiple containers run in parallel for the same app?
No. So what you'd do is you'd have multiple containers and you'd load balance it. So um, this is something, and actually, thank you for asking that question because it was something I meant to talk about, but I didn't add. So one of the advantages containerization also kind of brings you is before when you were launching applications, if let's say you were using like an Nginx server to run everything, you'd have one Nginx server run on one piece of physical hardware. If you needed to run more servers, it was an almost impossible prospect to run it on the same one unless you're doing some crazy things in the back. Now with containerization, you can basically run 10 instances of the same thing and then load balance your um, traffic between them. This means that like if your server can physically handle 10 containers and all that traffic, now you're using it much more efficiently compared to before having just one source of input and output. It also makes it a bit more fault tolerant because if one container goes down, the others will still take on the load and wait for this one to restart versus if it's your single physical server, when it goes down, you need to physically restart that thing, and that's going to be a couple minutes, even in cloud instances.
Awesome. Well, that brings us to the end of tonight's session. Thank you again so much, Neil, for the presentation, and thank you all for coming out to tonight's session. Before we go, I'm going to be reposting all these links that we've shared. And if this is your first time joining us, then welcome. Here at Tech Tank, we really want to create an inclusive space for tech enthusiasts to collaborate and build meaningful connections. We host a lot of networking events, social events, virtual discussions like these, and other career based virtual discussions as well, mentoring sessions, and more. We actually do have another virtual event coming up next Wednesday called Coding with Character. More info on that is available on our meetup page. But in general, if you do want more information about Tech Tank itself, head over to our website. Plugging the link in here now. Head over to our website and feel free to join our awesome community. That's all for tonight, folks. Thank you so much again, and we'll catch you in the next one. Have
Good
a good
night.
night, everyone. Bye.